The death of a low mass star, as we were talking about last time, results in what's called a white dwarf, right? It's white because it's extremely hot, so it's actually producing, usually light that's beyond the blue. So it's ultraviolet is probably where it peaks, or even higher. Anyhow, these things are extremely hot. So they're like as hot as like O and B stars, but their luminosity is usually hundreds of times less than the luminosity of the sun. And so the difference between these two, the sun or like an O or a B star and a white dwarf is simply size, right? If you look on the main, you look at the HR diagram. That's a great example right here. So this is after the planetary nebula stage that we were talking about, where the material just eventually goes out. Shells of material leave the dying star, and then what's left is essentially a carbon core that is extremely hot, right? So look at this. Imagine one of these white dwarfs over here. This is like a B type star right here. And so if you went up, I'm not going in a straight line. If you went straight up and you found a B type star on the main sequence, both of them have the same temperature. Let's say the B star and the white dwarf. But what's the difference, right? The B star is putting out hundreds to even 1,000 times the luminosity of the sun, and the white dwarf is putting out less than 1/100th the luminosity of the sun, right? Why is that? If you have a vertical line, two stars have the same temperature but different luminosities, and incredibly different luminosities in this particular case, it's just simply size. Right, it's literally the size of the star, and that's very important. So to remember that kind of thing. All right, so that's why we know that these things are white dwarfs. They're very, very hot, but they're putting out very, very very small amounts of energy compared to that of the sun. Right, 1/100th. Even some of them are as low as 1/1000th the luminosity of the sun. All right. So let's continue. There's an example that actually around, I know I said this last time, but around the brightest star in the sky, Sirius, is another star called Sirius B. It's a companion star, and it is extremely hot. In fact, the surface temperature is even hotter than Sirius, Sirius A, I guess you would call it, but its luminosity is incredibly low because it's just a tiny little dead star, right? And remember, the reason that these white dwarfs are glowing is just it's just temperature, the huge amounts of temperature that are cooling off, right? So when the star fused carbon in its core, the core is still really, really hot, and then these outer shells have been blown off into space, and so what's remaining, not quite to the core, but a good fraction of the way down to the core is remaining, and so you have a really tiny object, but it's extremely hot. All right, and the reason it stops is it's just not massive enough to fuse the next heaviest elements, right? Some stars would be more massive than this one when they're dying, and so they would fuse heavier elements. But stars that start off as relatively low mass stars, like the sun or Sirius, they'll never fuse anything heavier than usually carbon, but then there'll be some oxygen, some nitrogen, what's called a CNO cycle. So we're going to continue this. All right, so looking at globular clusters, we even find white dwarfs in globular clusters, right? So remember, these are really ancient stars. The globular clusters are regions just outside of the disk of the galaxy. They're in what's called the halo. These things are orbiting the center of the galaxy, as we're going to find out a little bit later. So we find white dwarfs in these stars because they're ancient, and so a star the mass of the sun, it would have had time to go through its entire life cycle and become a white dwarf. All right, let's see. So as the white dwarfs cools down, the size doesn't change very much, but they do get dimmer and dimmer. And it takes a long time. So we estimate in some cases trillions of years for these white dwarfs to completely become black dwarfs, as they call them. That's more of a theoretical thing. All right. So the outline of stellar formation and extinction can compare to observations. Okay. So this is something that we actually have a lab on this, which is dealing with looking at clusters of stars and finding what's called the turnoff point, the point where the stars would no longer be on the main sequence. And the further down the main sequence, the turnoff point, the older the cluster, right? And so this is one of the ways that we can tell how old the star clusters are. Let's see, blue stragglers in the previous HR diagram are not. They're not exceptions to our model. They're stars that have formed much more recently and probably merged from smaller stars. We're gonna find that does happen a lot more than you might think. That stars. Remember, like if you think about the Milky Way, and I know I've said this a number of times, but the Milky Way is, at least half the stars of the 200 billion stars in the Milky Way. At least half of them are binary stars. So it turns out that when binary stars, when one of the members of the binary star system dies, that'll actually affect what goes on with the other one, and we're about to see all that. Here's something from history. We have historical records going back over 2,000 years, as it says here, between 100 BCE and 200 200 BC. 200 what would be considered AD, but they like to use CE, which is called the Common Era. Right? We're in the Common Era right now. So during that 300-year period, it was noticed and it was recorded that the bright star Sirius was noticeably red. And if you look at it right now, it's definitely not red. It's a kind of a blue star, a bluish white star. And so we wonder, what happened, and maybe this has something to do with the Sirius B, which is the white dwarf. That's its companion star. So maybe Sirius B was going through its planetary nebula stage, and perhaps or just some of it was the planetary nebula, the planetary nebula stage. Maybe not at the beginning of the planetary nebula stage, but part of it anyway. Part of the matter that was in a shell around Sirius B and extended out beyond the orbit of where Sirius A was, and so that would have blocked some of the light and noticeably reddened the light, as was recorded historically. Of course, we don't have, other than eyewitness accounts during this 300-year period, we don't have like measurements or anything like that. Obviously, But the fact that it was red really does indicate that there was something going on, and we really think it was just what was going on had to do with Sirius B, not the it's just the light passing through one of those planetary nebula shells. All right, let's see. So when we look at so here's a star cluster. Happens to be a globular cluster. Don't forget the difference between globular clusters and open clusters, right? Open clusters, you have maybe thousands of members. Globular clusters, and they're new stars, right? The open clusters are relatively new stars, and they're in the disk of the galaxy. These globular clusters are outside the disk of the galaxy, and these are ancient stars. And in fact, the globular clusters themselves are close to 12 billion years old in some cases. Right. So anyhow, this particular thing, so this is looking at this turnoff point, and we see, as it says here, 3 distinct main sequences with increased helium content, which implies multiple generations of star formation. So when the earlier generations died, they left heavier elements, heavier than hydrogen and helium, and new stars formed. Now there wasn't a lot of this going on with globular clusters. It turns out most of the stellar evolution takes place in the disk of the galaxy, in spiral galaxies, as we're going to find out. There's another type of galaxy called an elliptical galaxy we'll get into later, but they have stars that are very similar to the stars in globular clusters, very low metal content stars. All right, so let's see, evolution of stars, more massive than sun. Okay, so now we're going to concentrate on stars that start their life more than, let's say, certainly more massive than the sun. So here's one that's about 4 times the mass of the sun, 10 times. When you get to about 10 times the mass of the sun or greater, things can become very, very different. All right, so let's follow this through. I'll probably have to go on to the next video to continue this. So the ones that are a little bit above where our sun is on the main sequence. So let's say 1.5, 2, 3, 4 times the mass of the sun. They follow very similar paths, right? They lose their hydrogen fuel supply in the core, and of course they leave the main sequence when that happens, and they go through this whole red giant stage, and kind of go back and forth. And in this giant area, let's see. So then high mass stars, like all stars, leave the main sequence when there's no more fuel. Let's see. You will get this hydrogen shell around, and the hydrogen shell will begin to burn, and of course that causes the star to heat up, and after it's left, it'll start to heat up, and then you'll get an increase, or the star will move in this direction, right? When it heats up, it's going this way, on the main sequence, right? Because things that heat up are going this way. So it starts to heat up, and then the helium starts turning into carbon, and then each of these is kind of like a pause, if you will, where the next heaviest element is being fused. All right, let's see, where am I? Let's see, stars on a different path. Okay, high mass stars will leave the main sequence when I just said that. Stars with more than 2.5 solar masses don't experience a helium flash. They kind of burn their helium in a gradual sense. Four solar mass stars Make no sharp moves on the HR diagram. There again,